All right, so we're in 5.3 now. Title is Selected Topics from Number Theory, and we're covering a few different just topics in this area. One thing I'm going to mention before we get into it, a common question people have in most math classes is, when am I going to use this? Where is this applicable in a real world situation? And although a lot of number theory, most of number theory, I would actually say, including some of these topics, do have direct applications in a number of areas. We've even mentioned cryptography in previous sections. Number theory also covers topics that don't necessarily have a direct application somewhere. We look at them more as curiosities. So to a pure mathematician, somebody who is only working to develop the area of math, whether or not the math that they're developing, applies somewhere right away, to the pure mathematician, a lot of what drives their work is just curiosity about relationships between mathematical objects, relationships between numbers. It's not a whole lot of interest to a pure mathematician if that's going to be used somehow. In fact, a lot of math that was developed this way, just math for the sake of math, found applications many decades after that math was developed. So all I'm trying to say here is that the topics that we're going to talk about here, some of them don't really have a whole lot of usefulness in the real world, but they are interesting yet nonetheless. They establish some interesting connections and relationships between numbers that are just kind of, some of them are sort of head scratchers, and like, why does this work the way that it does? It's just interesting. So that's my little intro into this section. Let's start working through some of these topics. So we've been talking about prime numbers and the concept of divisors for a while now, for the first two sections in this chapter. And I want to talk about something that we call a proper divisor. So if you have a natural number, a proper divisor of that natural number is just a divisor that's not equal to the number itself. So take, for example, the number 6. The divisors of 6, or the factors of 6, are 1, 2, 3, and 6. This is very easy to verify, and we've done this before. We've listed all of the factors or all of the divisors of a natural number. 1, 2, and 3 are going to be the proper divisors of 6. 6 is not a proper divisor because it's equal to the number itself. So that's what we mean when we're talking about a proper divisor. Now, we need that term to define the type of number that we're looking at first here. So a natural number is said to be a perfect number if it is equal to the sum of its proper divisors. So I use the example of 6 up here, and 6, it turns out, is a perfect number because look at the proper divisors of 6, 1, 2, and 3. If you add those up, 1 plus 2 plus 3, you get 6, the number that you were getting these factors from in the first place. 6 turns out to also be the smallest perfect number. And it turns out that perfect numbers are pretty rare. We don't find them very often. To show you something that's not a perfect number, take the number 9, for example. The divisors of 9 are 1, 3, and 9. That means the proper divisors would just be 1 and 3. But 1 plus 3 is 4, not the number that they came from in the first place, which was 9. So 9 is not a perfect number. Okay, let's look for other perfect numbers. Here, in this example, 28 is a perfect number, and we want to show that. What are the factors of 28? Well, 28 has 1 and 28. Remember, this is how we find factors or divisors. 2 times 14 makes 28. 3 is not a factor of 28. Remember your divisibility tests. You can add up the digits. 2 plus 8 is 10. And because 10 is not divisible by 3, then 28 will also not be divisible by 3. It is divisible by 4, however. 4 times 7. Between 4 and 7, I have the numbers 5 and 6. And it's easy to verify that neither of those are factors of 28. So here are all of the factors of 28. What I want to do is add up only the proper divisors, these guys right here. 1 plus 2 plus 4 plus 7 plus 14. Okay? Whenever I add up a bunch of numbers, I try to look for things that make 10. So for example, 1 plus 2 is 3, plus 7, that's 10. 4 plus 14 is 18. So this is like 10 plus 18, which is 28. Okay? Notice they added up to the number that they were factors of or proper divisors of in the first place. That makes 28 a perfect number. We're also asked to show that 30 is not a perfect number. So let's find the factors of 30. What are the factors of 30? 1 and 30, of course. 2 and 15. 3, it's a weird 3. 3 and 10. 4 is not a factor of 30, but 5 is. 5 times 6. And there's no natural numbers between 5 and 6, so I know that I've found them all. Now, let's add up the proper divisors. 1, 2, 3, 5, 6, 10, and 15. 1 plus 2, I don't know why I put a comma there, plus 3, plus 5, plus 6, plus 10, plus 15. What is this equal to? Let's see, 5 plus 15 is 20, 20, plus 10 would be 30. And then, let's see, I have 1 and 3 makes 4, plus 6, that's another 10, so that brings me up to 40, plus 2 is 42. This is not equal to the number that I used to find those factors, which was 30. So 30 is not a perfect number, but 28 is. We verified that up above. Okay, so we're going to talk more about perfect numbers. Right now we just talked about the definition and how to directly verify whether something is perfect or not. But there's actually other criteria that we could look at. And these numbers, these perfect numbers, have some interesting characteristics. So first of all, I had mentioned before that perfect numbers are pretty rare. We don't find them very often. In fact, as of today, we only know of the existence of 51 perfect numbers. That is a very small amount, especially when you consider that verifying that something is a perfect number, even though when you do it by hand can take a little bit of time, we have computers continually running, checking natural numbers. And we have ruled out trillions and trillions of natural numbers from this list. So the ones that are left, there's an infinite number of natural numbers to check. We'll never be able to check them all. But of those trillions of natural numbers, only 51 of them so far have turned out to be perfect. That's a very small amount. Okay. Other interesting facts that we've kind of discovered. Look at the two perfect numbers that we've found so far, 6 and 28. Both of those are even numbers. It turns out that all 51 of the perfect numbers that we have found so far happen to be even. We've never found an odd perfect number. But we've also never proven that no odd perfect numbers exist. There may be perfect numbers out there that are odd. We just don't know if they exist yet because we haven't found any. So that's an unproven conjecture in number theory. The conjecture states that all perfect numbers are even, but we just don't know if that's true yet or not. Interestingly enough, for all of the perfect numbers that happen to be even, we have an interesting connection between those specific perfect numbers and the Mersenne primes that we talked about in section 5.2. So remember the way that we define a Mersenne number, mn, it's equal to 2 to the n minus 1. So if n is equal to 2, then this would be 2 to the second power minus 1, which is 3. Or if n is equal to 4, this would be 2 to the fourth power minus 1, which is 15. Those are Mersenne numbers. If this number happens to be a prime number, then we call that a Mersenne prime. And you'll recall that in section 5.2, we talked about how this can only ever be a prime, a Mersenne prime, if n is also a prime number. Although that's not a guarantee, because we've seen that there are examples where n is prime, yet this is composite. But anyways, what's the connection between these two things? Well, Euclid, that Greek mathematician from a long, long time ago that we've mentioned before, proved this. If 2 to the n minus 1 is a Mersenne prime, so if this is a prime number for some natural number n, let me say that differently. 2 to the n minus 1 is a Mersenne prime if and only if 2 to the n minus 1 times that Mersenne prime, 2 to the n minus 1, is a perfect number. Okay. Now, back in Euclid's time, they didn't know what a Mersenne prime was, or they didn't have that terminology for it because Marin Mersenne came centuries after Euclid. But they still dealt with expressions and numbers of this type. So one condition implies the other and vice versa. If this is a Mersenne prime, then this number is perfect. If this number is perfect, then that's a Mersenne prime. What that means is we have a direct correlation between all of the Mersenne primes and all of the even perfect numbers. So the fact that we know that there are 51 perfect numbers means we also know that we only know about 51 Mersenne primes, and they are directly correlated. So I'm going to use an example to kind of flesh this out a little bit more. I would like to show that 496 is a perfect number. Now, and there's a hint here, consider the Mersenne prime. Now, I could do this directly using what we did over here. I could find all of the factors of 496, add up the proper divisors, and then show that that's equal to 496. And that wouldn't be the worst thing in the world, but 496 is a larger number than I worked with in those previous examples, and so finding all of the factors would take a little more time. But this result gives me an alternative way of checking that 496 is a perfect number. Rather than do what we did in the previous example, add up those proper divisors, I am going to take this hint and consider the Mersenne prime M5. So M5 is equal to 2 to the 5th power minus 1, which is equal to 32 minus 1, or 31. Okay? So M5, and we've seen this already, is a Mersenne prime. Okay? It's guaranteed to be a Mersenne prime. That means if I take 5, which was the n, and plug it into this expression, this is guaranteed to generate a perfect number simply because that is a Mersenne prime. That's what this is saying. So let's do that next. 2 to the 5 minus 1 times 2 to the 5 minus 1. This is equal to 2 to the 4th power times, we just evaluated this up here, that's 31. 2 to the 4th power is 16, so we have 16 times 31. Multiply this out either in a calculator or by hand. It's easy enough to do by hand. You'll see that this is 496. Notice it's the number that we were checking on up here. And the fact that M5 is a Mersenne prime, 2 to the 5th minus 1 is a Mersenne prime, according to that theorem we just talked about that Euclid proved, guarantees that this will be a perfect number without having to check the sum of its proper divisors. Now, you are more than welcome to find the proper divisors of 496 if you want and add them up. You should see that it comes out to 496, which makes it a perfect number. Okay? All right. We're moving on now to a related concept. We say that a natural number is deficient if it is greater than the sum of its proper divisors, and we call it abundant if it is less than the sum of its proper divisors. And after doing an example, I'll kind of help you make sense of why we call these things by these names. So first of all, if a number is not perfect, if a natural number is not a perfect number, then it's one or the other of these. Because if it's not equal to the sum of its divisors, then it's either greater than that sum or less than that sum. So that's what these two account for. Let's start with 36. I want to find all of the divisors of 36. 1 and 36. 2 and 18. 3 and 12. 4 and 9, and then 6. That would be the last one. Okay, now what I want to do is add up the proper divisors, so everything except for 36. 1 plus 2 plus 3 plus 4 plus 6 plus 9 plus 12 plus 18. Okay, 12 plus 18, that's 30. 9 and 1 is 10, so that makes 40. 6 and 4 is 10. Now we're up to 50. Then 3 and 2 makes 5, so that's 55. 55 is greater than 36. So in this case, the number that we were checking on, 36, is less than the sum of its divisors. Which of these two did that account for? Well, we say that a number is abundant if it is less than the sum of its divisors. So this is an abundant number. Okay, 36 is abundant. 15, let's check on that. What are the divisors of 15? 1 and 15, 3 and 5. That's it. That's all that it has. Okay, so let's add up its proper divisors. 1 plus 3 plus 5, that's 9, which is less than 15. Or said differently, 15 is greater than the sum of its divisors. That's what we call a deficient number. Now, the terminology here might seem a little bit confusing because deficient generally means little or not enough of something. Abundant means a lot or sometimes even too much of something. So it seems a little bit weird that in the definition for the term deficient, we see the word greater. It doesn't seem like deficient should have a definition involving the word greater. It feels like greater should go with abundant. But here's the reason why. The fact that 36 was less than the sum of its divisors, in a certain sense, implied that it had a lot of divisors. Notice how big this list is, or this list here. Because there were so many proper divisors, it added up to a number that was larger than 36 itself. So the abundant part is not saying that 36 is a large number compared to this sum. It's actually saying that it has an abundant number of factors in this way of thinking of it. So that's the idea behind the term abundant. In this sense, notice where 36 had a lot of proper divisors, 15 only had 3 proper divisors. And it turns out that they were too small to add up to a number that exceeded 15. So we call this deficient because it doesn't have a lot of divisors the way that 36 does. Okay? Now here's a good question. Do there exist any abundant prime numbers? Based on the discussion that we just had, we should expect the answer to be no, because remember, abundant in a kind of a intuitive sense means that a number has a lot of factors. But primes, by definition, only have 2 factors. In fact, any prime number, if p is prime, then its only proper divisor is 1, right? Because the only divisors of a prime number are 1 and the prime number itself. But the prime number itself is not one of its proper divisors. So the only proper divisor of a prime number is 1. And we've already seen all prime numbers are larger than 1. The smallest prime number is the number 2. So if I add up all the proper divisors, there's only one number in that list. So the sum of those divisors is just 1. Since 1 is less than the prime number p for every prime p, then p is deficient. So that sort of shows that every prime number is a deficient number. Okay? All right, let's move on. Here we go. Moving on to another interesting topic. And again, perfect numbers, deficient numbers, abundant numbers. If you're asking the question, what is this useful for? Right now, for our purposes, nothing. And we're not going to try to establish anything that they're used for. It's just curiosities. It's just interesting little characteristics that natural numbers can have. Here is another interesting characteristic that we can talk about. And this is not a property of a single natural number, but rather it's a relationship between 2 natural numbers that might be possible. So 2 natural numbers, a and b, are called amicable, or we can also call them friendly numbers. Seems like a ridiculous term to be talking about in a math class, but we do have a definition for this. 2 natural numbers are called amicable or friendly if the sum of the proper divisors of a equals b, and the sum of the proper divisors of b equals a. Notice this is kind of similar to the definition of a perfect number, but this time we're not trying to show that the proper divisors of a number equal itself. We're trying to show, in this example, for example, I want to show that 220 and 284 are amicable or friendly. That means I'm trying to show that if I take the proper divisors of 220 and add them up, I'll get 284. But not only that, if I take the proper divisors of 284 and add those up, I'll get 220. It has to go both directions for them to be called friendly. Other word wise, that's a very one-sided friendship. So 220, let's start there. What are the proper divisors of 220? It has a lot. 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, 110, and then it's not a proper divisor, but I'll just include it in the list, 220. Okay? Notice this time I'm giving you all of the factors. We've done a few examples of trying to find these by hand. I would find 1 and 220 first, and then 2 and 110. But to save some time, I'm just giving you the list here. What are the proper divisors of 284? It doesn't have quite as many. It's 1, 2, 4, 71, 142. And again, it's not a proper divisor, but I can still write it 284. That's the complete list of factors. Okay, if I were to add up all of the proper divisors of 220, 1 plus 2 plus 4 plus 5 plus 10 plus 11 plus 20 plus 22 plus 44 plus 55 plus 110, you would find, and you're welcome to try this either by hand or in a calculator, you would find that they add up to 284. That's checking one direction. Now, if I take the proper divisors of 284, 1 plus 2 plus 4 plus 71 plus 142, less add-ins, less numbers to add up, but you would find that these add up to 220. So it goes both directions. This makes these numbers amicable or friendly. Okay, that's all we're really doing with that concept. Just another term, another relationship that numbers can have that's kind of interesting. I will say that it's very uncommon to find these amicable pairs of numbers. They do not show up very often, kind of like perfect numbers. Okay, moving on to yet another topic. This one is called the Goldbach conjecture, and this is actually one of the most famous unproven conjectures in number theory and actually all of math. It's one of the most well-known and famous of those. So famous, in fact, that there's actually a movie, and I'm forgetting the name of the movie now. It was a foreign film that was made kind of around the idea of the Goldbach conjecture. It was fiction. The main character, I think, thought he had proven it or something like that, and yeah, I wish I could remember the name of that movie, but it's just very famous. That's all I'm trying to say. Part of what makes this famous is that the conjecture is actually very, very easy to understand. Yet, despite how easy it is to understand, it's been impossible for us to prove so far. We haven't been able to prove it. So what is the Goldbach conjecture? Well, the Goldbach conjecture says that every even number greater than 2, so that would be 4, 6, 8, 10, and so on, can be written as the sum of two prime numbers. So, as an example, a couple of examples, we want to verify Goldbach's conjecture for these two numbers, 16 and 40. Both of these are even numbers, and that's the numbers for which Goldbach's conjecture applies. I want to show that 16 can be written as the sum of two prime numbers. Now, I would go so far as to say that they have to both be odd prime numbers. Remember, the only even prime number is 2. And if you're going to add up an even number plus something else and get an even number, then that other number would have to be even as well. Because otherwise you're adding an even and an odd, and that always makes odd. But if 2 is the only available even prime number, then the only way to add two even primes is to add 2 plus 2, which is 4. Neither of these are 4. So it kind of only makes sense to look for odd primes. The smallest odd prime number is 3. And 3 plus what makes 16? Well, 3 plus 13 is 16. Both of those are prime numbers. We saw that in our sieve of Eratosthenes example back at the beginning of chapter 5. So that's one way of doing this. Is it the only way? No, it's not. Notice that 5 plus 11 is also 16. I don't need to find two different ways. I've only been asked to verify the conjecture, but my reason for showing you two in this example is just to illustrate that it's not saying that there is only one way, of writing every even number as a sum of two primes. It's just simply saying that at least one such sum of primes will equal that even prime number. So 40. Can I think of any numbers that, any prime numbers that add up to 40? Well, if I start with 3, again, my smallest prime number, 3 plus what makes 40? 3 plus 37 is 40. And again, if you go back to your sieve of Eratosthenes, you'll find that 37 is also prime. I'm only going to do one example in this case because that's all I'm really asked to do. But interesting, right? So again, we have not proven this. What would it take to show that Goldbach's conjecture is false? Well, if you want to prove a mathematical conjecture false, the typical way to do that is to find a counterexample, which is an example for which the conjecture fails. So what that would mean in this case is I would need to find an even number greater than 2 that cannot be written as the sum of two prime numbers. And there's ways to verify that. You know, the only way you're going to get a number to equal a sum of two primes is, for one thing, if those two primes are less than this number. So that gives you a finite list of prime numbers to check for every even number that you're trying to verify, either passes or fails this little test, this conjecture. And again, like I had said with perfect numbers, we have computers, very, very fast computers, checking this for us. And they have been continually checking this for us for many years now. And we have yet, even after going through trillions of natural numbers, we have yet to find a single example that fails Goldbach's conjecture. All of the even numbers that we've checked using, computer programs have been verified to pass Goldbach's conjecture. That does not mean that Goldbach's conjecture is true, because there are an infinite number of even numbers out there. It does not matter how fast your computer is. We will never be able to check all of them. So we have to have a different way of proving that, and we have not figured out how to do that yet. Okay, so that's very famous conjecture in number theory. All right. I think I'm going to do the rest of this in a follow-up video.